Hi, welcome to my channel, Jabber Time. Today I'm going to go over quadratic function forms. This is part 2. I'm going to go over the standard form, the vertex form, the factored form, and the benefit of each. For example, the standard form mainly talks about the c, which is the y-intercept. For the vertex form, the main part is the h and k, which is the vertex, where you could tell that you have a maximum or a minimum at that point. The factored form, the main part is the zeros or the roots, where the graph crosses the x-axis. Let's get into it. Before we start, we need to be aware of the parent function y equals x to the second, where a equals 1. That means it's not vertically stretched or compressed. It's just like the normal opening of y equals x to the second, with the vertex at 0, 0, and goes through the point 1, 1. So if there is no vertical stretch, this is going to be like 1, 1 as a box. So if I move this and I use transformation, and I move this point to this point, the second point will be right here. All right. So if you see this as going just 1, 1, of course you have to pay attention to the scale on the x and the y axis. That means a is 1. The standard form is ax squared plus bx plus c. Of course, a cannot equal to 0, because if a equals 0, this term will cancel, and now you don't have a second degree function, you just have a linear equation. Same thing for the factored form, a cannot equal to 0, and this is how we write it down. The vertex form, this is how we write it down. Also, a cannot equal to 0. Notice that in all of them, a is the same. They're having the same letter a, or coefficient, leading coefficient term. And if a is positive, that's in all of them, a determines if the graph opens up or opens down. Let's give you more details about each one before we start going over examples. I have enough examples in this video. Hopefully it's going to be helpful. So here's the 3 forms, and they all share the same thing down here, which is if a is positive, greater than 0, the parabola, which is the shape of the quadratic function, opens up. That means we have a minimum at this point. If a is negative, the parabola will open down, and of course we're going to be talking about a maximum value for the function at this point, which is the vertex. The standard form, ax squared plus bx plus c. The axis of symmetry, to find it in the middle, which is x equals minus b over 2a. The vertex will be minus b over 2a, and whatever comes from the equation as an output. The y-intercept that I mentioned is the c part, which makes sense because when you cross the y-axis, your x's are 0. So if you plug in 0 for x here and here, that's what you have left for you, which is c. So c will be the y-intercept, which is a good point to know if you're graphing the function by hand. The x-intercepts, to find them, you need to set y equals 0. And after that, either you use factoring techniques, or if you can't factor, because sometimes it's hard to factor, especially with decimals and irrational numbers, so you need to use the quadratic formula. The factored form. The axis of symmetry will be where the locations of the zeros R1 and R2 are. You have to go halfway in between. If you could see that, you don't have to do the whole thing and divide, add them and divide by 2, because that will tell you the middle point between them. So it's x equals R1 plus R2 over 2. The vertex will be, of course, the x value of the axis of symmetry, which is the value right there, and the output, whatever that comes out using the equation. The y-intercept, to find it, you need to set x equals 0, plug it in, and just do the math and multiply the 3 numbers. For the x-intercepts, those are straightforward from R1 and from R2. The vertex form. The axis of symmetry will be x equals h. The vertex will be h and k. That's why it's called vertex form, because it's written on the vertex or leads you to the vertex straight forward. The y-intercept, you need to substitute x equals 0 and finish calculating. For the x-intercepts, same idea like right here. I have enough examples in different types. The only thing that is not covered in this video is completing the square. Okay, I'll have it, of course, in the different videos. Find the equation of the parabola with vertex given to me as 5, 2 and passes through the point 4, 9. Those are the given information. Well, since they mentioned the vertex, I think the best way is to use the vertex form. I have the vertex in green and I have the point in blue. I like to distinguish things to make it outstanding and clear to focus on while you're watching the video. So I'll be using the vertex with green numbers and the point with blue numbers. Here's the vertex form that we agreed on. To solve for A, this right here, which is missing, we don't know it. All what I need to do is plug in h and k, which is 5 and 2, and plug in for x and y, the 4 and 9. As you can see, the colors tells you where to get them from, and that's how we do it. Notice that everything is given except A, and with calculations, I have 4 minus 5, which is negative 1. Square will be 1. So I have 1a plus 2 equals 9. Subtract 2 from both sides, I get a equals 7. And now we are ready to write the equation. And that should do it. That tells you that the vertex is 5 and 2. It's exactly similar to x minus h to the second plus k. A came up to be 7. You could double check and plug in 4, 9 to make sure. Here's another example. This time they gave me 2 points. They're called roots. That means where the graph is going to cross the x-axis, they gave me the 2 points, and they gave me a third point because I need the third point to find A. So the roots are negative 2, 0 and 4, 0. Comparing it to R1, 0 and R2, 0, I end up with R1 equals negative 2 and R2 equals 4. So the graph crosses the x-axis at negative 2 and 4. Of course, if I graph the point 1, 6, I'll know that if it opens up or down, but that's not the point. So I have 1, 6 in blue, the other point given to me. I'm going to use the factored form because they gave me the roots. That's the best option that I have. For R1 and R2, I'm going to use the numbers in green, negative 2 and 4. Of course, you have to pay attention to the subtraction and the minus sign. And for x's and y's, I have 2 x's this time. I'm going to use 1 and 6, just like that. Now, as I said, you have to pay attention to the minus sign. 1 minus negative 2, because R1 is negative 2, will change to 1 plus 2. Doing the math, I end up with negative 9a equals 6. Divide both sides by negative 9. Simplify, you get negative 2/3. And the answer is as it shows right here. Now, those are two good examples, but I want to give you more examples with graphs so you could analyze between graphs and functions, the benefits of each and what each tells you. The graph will tell you something, the equation will tell you something. Let's see back and forth to see the benefit or knowing enough about the equation and the graph. Here's an example. I could talk for a long time here about the graph, And I could talk also about here, but I just want to stay focused with you with the notes, and we'll move on. This is factored form. This is a parabola that opens up. Comparing this to the factored form in general, I could tell that a is 2, and I could tell if I rewrite this as x minus -1, that r1 is -1. Same idea here, you have to pay attention. R2 will be -5, not 5. What makes it 0 is -5, not 5. Okay, so I have A and R1 and R2. That confirms R1 and R2, which is -1 and -5. And the scale here is going by 2. The scale here is going by actually half. So it's kind of hard to see the 1, 1 idea that I mentioned earlier. But they gave me A equals 2. That's the stretch factor. So we have a minimum here if they ask you for the minimum, because the graph opens up, because A is positive. Axis of symmetry, the graph shows at x equals -3. If you do it from the equation, I get R1 plus R2 over 2. And doing the math, -1 plus -5 over 2 will be -6 over 2. And that is actually -3. At x equals -3, we have an axis of symmetry. Now let's see the vertex. The vertex looks like it's at -3 and -8 for the y. To find it using the equation and what we know about the vertex form, we're going to take this value that we came up from the axis of symmetry and find its output. It's -3. F of -3 will have to plug it in, just like that. Doing the math, I end up with 2 times -2 times 2, which is -8, as the graph shows. So that's the vertex. And we have a minimum at this point if they ask you for maximum and minimum. And the minimum is at x equals -3, and the value equals -8. Let's take another example. This right here shows enough, but I want to stay focused and I have enough for you. As you can see, I'm dividing the screen into parts. It's opening down. A is native. Yes, A is native. The y-intercept is about there, a little bit more than 20, and it shows here 21, which is not bad. It does agree. Okay, let's see the details. First of all, the C value, which is 21, that's the y-intercept, 0, 21. A is negative, so the graph opens down, and we have a maximum. The axis of symmetry will be x equals minus b over 2a, and we have to be careful with reading a and b and c. Minus b is -1, so it's minus -1, the opposite of -1, over twice a, and a is -5, as mentioned right here. Simplifying this, that's a +1 on top, -10 at the bottom side, which is just -1/10 or -0.1. And it shows, yes, it's about right there. The axis of symmetry, right there. To find the vertex, we take this number and plug it in, which takes time to read on the screen, but I have the work done for you. You just plug it in and take your time step by step. And with all the calculations, I have 21.05. It looks like, yes, the maximum or the vertex is at this point, which is -0.1, -1/10, and 21.05 right there. Now, this is my equation. This is the standard form. Comparing it, I have A and B and C. A -5, B is -1, and C is 21. To find the x-intercept, this point here and this point here, as you can see, they're not exact. They're probably decimals. Let's see. To find the x-intercept, we set y equals 0. So having y equals 0, the output, the whole thing equal to 0, it will be hard to think about factoring here, because 21 and 5, I have to go like 21 times 1. That's not gonna work. 21, maybe 7 times 3. That's not gonna work. That's not gonna give me these coefficients like the -5 and the -1. So let's use the quadratic formula. Minus b plus minus square root of b squared minus 4ac over twice a. To do this and save some time, usually we take care of the inside part here under the square root, which is called the discriminant, b squared minus 4ac. Once you find it, it tells you if you have two real roots or one root or imaginary roots. One root as repeated root or two imaginary roots. So let's take care of b squared minus 4ac. Plug in the numbers, -1 for b, -1 for b, times minus 4ac, a is -5, and c is 21. I have 421, which is positive. Positive, that means I have two options here and I could go on. With that, simplifying -10 here and changing this to +1, breaking it into two pieces, I have it this way. Now I have two options, plus, minus. Once I could add and once I could subtract. And I do the math, simplifying, saving some time from the recording. I have it pre-written. x1 is about -2.15 and x2 is about 1.95. Yes, it looks like 1.95 here and -2.15 right there. That should do it for this problem. Let's take another one. When you have it f of x equal 2 times x minus 1 times x minus 5, that's a factored form, tells you that a is 2, opens up, +2, and the roots are 1 and 5. 1 and 5. Let's write more details and discuss the difference or the benefit of knowing this and graphing or comparing to the graph. Now comparing it to the factored form, I could tell that a is positive, which means it opens up and we have a minimum at the vertex point. The roots, comparing these sets, I have r1 equals 1. Right after the subtraction I have 1. Right after the subtraction I have r2, which is going to be called 5. Axis of symmetry will be the average of these 2 points to go in the middle. I could see it from the graph, but doing the math, it's 1 plus 5 over 2, which is 3. So x equals 3 will be my axis of symmetry right there. The vertex shows right here at 3, -8. Let's just do the math. Take 3 and plug it in the original equation. Plug in 3 here and plug in 3 here. Do the math. Yes, it confirms that the output is -8. So the vertex, yes, it's 3 and -8. So we have a minimum value at x equals 3 and the value is -8. Here's another one. This one opens down but doesn't cross the x-axis or touch the x-axis. This is a vertex form, so I'm going to compare it to the vertex form. Rewriting this as x minus -2 to make it +2, or comparing it, I could tell without making mistakes that h is -2 and k is -4, as it shows right here. Now, because a is -1, it's going to open down, and we're going to have a maximum at the vertex. The vertex is straightforward from h and k, which is -2, -4. Yes, it does show that. Pay attention that the scale here on the x is going by 2s, and on the y it's going by 4. The axis of symmetry will be x equals h. In this case, it will be x equals -2. Yes, it does show that. Axis of symmetry right there. The maximum at x equals -2, and the output is -4, which is the k value. The y-intercept, let's see the y-intercept here. Plug in x equals 0. Just plug in here x equals 0 to find the y-intercept. Do the calculations. I have -8. So the y-intercept is at 0, -8. To find the x-intercepts, which the graph doesn't show any, we're going to set y equals 0. To set y equals 0 and try to solve algebraically, look what happens. By moving this to the left or adding x plus 2 to the second, this will cancel. Instead of getting rid of -4, I moved this to make it positive. Now I have x plus 2 to the second equals -4. But nothing that you could square will give you negative, so that doesn't have a solution. You can't find a number, multiply by itself, and get negative number. So no x-intercepts, as the graph shows. Let's take another similar problem, just for more practice. This time it's 4 inside and the 2 outside. Again, I'm going to compare it to the vertex form. I'm going to take my time and read h and k clearly. H is -4, not 4. A is -1 and k is -2. Since a is negative, it's going to open down. We see that. We have h equals -4 and k equals -2. And that is my vertex. -4, -2. Axis of symmetry, the graph shows at x equals -4. Well, it is x equals h, which is x equals -4. Yes, it does agree. Here's another one. This one is a little bit different because it only touches the x-axis. Alright, that's like the parent function shifted to the right 1 unit, pretty much, as you could see. Okay, let's see what we could do for this problem. I'm going to use the vertex form. So a is 1. If I want to compare this and rewrite it in detail, I could see that h is 1 and k is 0. Because I have nothing here being added, that should be a 0 value for k. So a is 1, it's positive, opens up, we have a minimum, okay. H is 1 and k is 0, that's the vertex. Yes, it's at 1 and 0. To find the y-intercept, we set x equal to 0. Just plug in 0 for x. 0 minus 1 is -1, but you still need to square it, so it's 1. So the y-intercept is at 0 and 1. Yes, it looks like it because they're going here by 2. That's 2, 4, 6. So halfway will be 1. Yes, it looks like it's 0 and 1. To find the x-intercepts, which the graph shows only 1, we set y equals 0. And now my y is 0. Well, x minus 1 to the second equals 0. That's another way to see it. But I don't have too many options. Like, you know, if this is x minus 1 and this is x minus 5, yeah, I'll set each one equal to 0 to solve. But it's the same thing. So we call it repeated factor, repeated root at x equals 1. When it's a repeated root, the graph doesn't cross. It bounces off the x-axis. So you have one x-intercept at 1, 0. We have one root at x equals 1, which is with multiplicity 2. Because that's like 1 from here and 1 from here. It's like repeated twice. we just write 1, but it's good to know that we call it with multiplicity of 2. Graphically, that's not a normal root that you cross the x-axis and you go to the other side. No, you just touch the x-axis and bounces off. The graph does not cross the x-axis. It bounces off. Alright? Let's take more detailed graphs. This graph has a lot. Pretty much they gave me everything. They gave me the axis of symmetry. They're pointing to it. They gave me the x-intercepts. They gave me the vertex. They gave me the y-intercept. There's a lot with this graph. Speaking with the y-intercept, I could think about the standard form. Thinking about the x-intercepts or the zeros, I could think about the factored form. Thinking about the vertex, I could think about the vertex form. So I'm going to start with the vertex form. The vertex shows 1, -4. 1, -4. And if you pay attention to the scale, they're going 1, 2, 3, 4. So by 1 on the x, and 1, 2, 3, 4 by 1 on the y. But look at these 2 points. That's exactly like my first graph, my second slide or third slide. That shows if this is 1, 1, it's like you're moving the graph from the original place where the vertex is at the origin down here, translating to the right and down. So still the scale factor or the stretch factor still 1. So I'm going to use 1. That's what I meant. You compare it to y equals x to the second. See the 1, 1 here? Alright. So a is 1. The axis of symmetry is x equals h. And x equals 1 will do. It's right here in red. The y-intercept is x equals 0. That's when x equals 0, I mean. I think I said y. When x equals 0, you just plug it in. Do the math. 0 minus 1 to the second. It just minus 1 to the second, which is 1. So you end up with 1 minus 4. And that's -3. It looks like, yes, the y-intercept is when x equals 0. And the y value is -3. Now, to find the x-intercepts, we're going to set y equals 0. I could see them from the graph, but let's do the algebra. Set y equals 0. Add 4 to both sides. Rewriting it the other way around, just like the normal way we're used to. Now, taking care of the square root of both sides, I end up with x minus 1 equals plus minus square root of 4. Adding 1 to both sides. Now I have 2 options. It's 1 plus minus 2. Square root of 4 is 2. So either you add 1 plus 2 or you subtract 1 minus 2. Once you do that, I get minus 1 and 3. That's a minus 1, and that's a 3. So the x-intercepts are at -1, 0 and at 3, 0. Let's use the factored form. For the factored form, I mentioned on the first or second slide that a is the same a in the vertex form, the factored form, and the standard form. So if we agreed on a to be 1 from the start, I'm going to use 1 right here. X minus -1, that's my first root. X minus 3, 3 is my second root. Taking care of this and calling it y for the convenience. 1 is gone. I don't need to display the 1. Multiplying this using the box idea, or you could use any method that you want, like the FOIL. I have x times x, x to the second, x times 1, which is x, negative 3 times x, negative 3x, negative 3 times 1, negative 3. We combine the like terms, and we end up with x to the second minus 2x minus 3. Now you have the whole package, which is how the standard form for this equation looks like, which is x squared minus 2x minus 3. The factored form, which is right here, and the vertex form, which is right here. So that's like 3 in 1. Here's another example. Seeing this as a vertex form, I could tell that the vertex is 3, 1. So I wrote 3, 1. Now to write it down, we're missing a. So it's x minus 3, x minus h to the second plus k. To find a, I'm going to use the point right here, which is 0, 7. Plug in 0 for x, 7 for y. Do the math to solve for a. I have negative 3 to the second, which is 9. 9a plus 1 equals 7. Subtract 1 from both sides. I get 6 equals 9a. Divide both sides by 9. 6 over 9 simplifies to 2/3. And now I have the equation. It's y equals 2/3 multiplied by x minus 3 to the second plus 1. Here's an example. Y equals x to the second plus 4x plus 3. And as you could see, I have the graph and it shows enough details. The y-intercept is the c value, which is 3. We could see that right there. A equals 1 opens up. The axis of symmetry from the standard form, we read it as x equals minus b over 2a. Doing the math, I have minus b, the opposite of b, minus 4 over twice a, where a is 1, simplifies to negative 2, and the graph shows that. It's going with a scale of 1, as you can see, 1, 2, 3, 4, 1, 2, 3, 4, and that reads as x equals negative 2. Now, the vertex will be negative 2 and the output of negative 2 to find that location. Doing the math, I have negative 1, which confirms on the graph. The vertex is negative 2, negative 1, and we have a minimum at negative 2 with a value of down to negative 1, y value. That's a minimum y value. Before I move to another graph, another example, just want to mention that looking at the scale here, it's going by 1 on both x and y axes. And you see this box right here? This is like what I mentioned earlier, 1, 1. That confirms that the scale factor, not the scale factor, the stretch factor, which is a, the leading coefficient of the leading term, is actually 1. That also shows on the equation itself. So you could tell from here that we have a equals 1. Of course, we could discuss more about, the factored form and so on, but that's good enough for this problem. Let's move on. For this example, I have the equation in vertex form, and I see the graph and they're pointing to the vertex. Comparing it to the vertex form, I could see that a is negative 3 and h is negative 2 and k is 4. A is negative 3, so it opens down and we have a max. Axis of symmetry from the vertex form will be x equals h, and that is negative 2. You have to be careful. It's not 2, of course. comparing it to x minus, it will be -2. And the graph shows it. To find the vertex, you take -2 and plug it in, or compare it right there. It's already given to me, by the way, which is 4. Now, here's a comment. Notice that the graph shows that a is not -1, it's actually -3, as the equation shows. Because the scale is going 1 to 3, 1 to 3, which is the normal way, so it's not going to be misleading. If this is upside down and it's not being stretched vertically or compressed, this is the vertex. This will be my second point. But look, it's all the way down here. So it's not 1, 1, it's 1, 3. That kind of confirms that a is -3. Just a comment to let you pay attention to. So we have a maximum at this point when x equals -2 and the maximum value equals y equals 4. Here is a vertex form with a graph. H and k will be -2 and -3. Comparing it to the vertex form, we want to show that a is half. So to solve for a, I'm going to use 0, -1. This point right here is clearly to me on the graph 0 for x, -1 for y. You don't want to pick points like you cannot tell exactly on the graph. Like for example, this one doesn't look like 1, 1 or goes close by, but it's not. So I think 0, -1 is a good point. Plug in 0 for x, -1 for y. I'm saving you the time to read all these numbers, and I have everything displayed for you ahead of time. Doing the math, that's 4a. -3 equals -1. Add 3 to both sides. Divide both sides by 4. I have a equals half as it shows right here. So it's kind of hard to read the half from the graph, but there is ways of confirming or finding a. So that's what I have, which agrees to exactly what they gave me. Okay. Now, rewrite the standard form, which is given to me as 2x squared minus 6x plus 7, in vertex form. Well, to do that, we sometimes what we call it complete the square. I'm not doing the process right here of completing the square, even though it's similar. That will be in different videos, all right? But in the meantime, because our topic right here on the first slide, it's the quadratic function forms, standard, vertex, and factored form. So I'm just going to stick to that topic and show you the connection. To make a connection between the standard form and the vertex form, you know, we remember the following. Once you identify ABC, A is 2 and B is -6 and C is 7, knowing that it opens up, this is what I mean. To make a connection between the standard to the vertex speaks h and k. Well, how do you find h? It's minus b over 2a, so that's a connection between the standard speaks a and b, the vertex speaks h and k. But actually, if you go back to complete the square, that's part of the game. You take the coefficient of x, you divide by 2, you add it to both sides, and so on, after you make the leading term equals 1 for x. Well, enough of that. I just want to give you an idea that, yes, it connects to the complete the square. It does. So, in the meantime, let's just make a connection between vertex and standard. So I have x equals h, which is minus b over 2a, minus b, which is -6, over twice a. Doing the math, I have 3 over 2. Well, if you have the h part, how do you find the k part, which is the output? You just plug in 3 over 2 in the function. I have 5 over 2 as an output. Now here's my vertex. I mentioned also earlier that we don't need to worry about A. A would be the same in the standard, A would be the same in the vertex, A would be the same in the factored form. So we're not going to worry about A. A is 2. Why? It's right there. It's given to me. I have the vertex. I have A. I'm done. All what I need to do is write the equation. Take a look. That's it. So with that in mind, and identify the maximum minimum value, here's the minimum value. Because the graph opens up, we have a minimum at x equals 3 over 2, which is at x equals minus b over 2a, and the minimum value will be the output of the vertex k, and that's 5 over 2. Hopefully that was clear and helpful. Find the domain and range of this quadratic function. Well, this one opens down. As you could see, it opens downward and has a maximum value at the vertex, of course. So we need to find the vertex. We need to find the maximum value because that's part of the range. But here's a comment that I'm trying to make it outstanding here, that you need to keep it in mind as a note. As with any quadratic function, the domain is all real numbers. You know, when you graph a function like this one, you know, most of the graphs that I have collected for you, it shows the graph and it shows the arrows at the end. That tells you that it keeps going. Once you graph a parabola on a graphing calculator, it doesn't show the arrows. Sometimes for some reason students, they think that it stops right there. No, it keeps going. You could plug in any number. Just keep this in mind. Now to find the vertex, because we need the vertex to find the maximum, we just do the math. To find the x component, which is minus b over 2a, since I have the standard form, I'm using minus b over 2a, minus 9 over twice negative 5, negative cancels, and I have 9 over 10. Plug in 9 over 10 to find the output at that location, which is the k part or the vertex y coordinate. The maximum value is at 61 over 20. So the graph opens down and reaches to this point, to this value, which tells me that the range is all the way down up to this level. And that's how we write it down. All the way from negative infinity, of course we can't include negative infinity, up to 61 over 20 included. That's my range, but the domain is all real numbers in every single parabola. Here's more examples, quick examples, domain and range for 2 examples. X minus 2 to the second plus 1, and this right here. Well, this one, the domain is all real numbers. You just have to keep this in mind. The range is from 1 up. Why 1 up? Well, this graph opens up. A is 1. So if it opens up, it's going to go from this point up to infinity, but this point is the k part for the vertex 1. From 1, including 1, up to infinity. Let's take a look at this one. This one is upside down. The domain is all real numbers. And the range reaches up to 4 because of this 4. So we're going to write it from negative infinity to 4, including 4. Now I think I have enough examples that talks about the 3 forms. And you might wonder sometimes, like, why do you study quadratic formulas and factoring and vertex form, standard form, and so on? Well, the main reason is the applications and the real life scenarios. Math is the language of life, and it's not the other way around. It's not like we create math, we create equations so we could go outside and use them. It's actually in life. pretty much a lot of things in life behaves with patterns that could be translated to math formulas. There is things in life that if you graph it goes up then back down as a parabola. Let's get into it and show you just one application. In the future I'll be adding other videos, and I'll be calling a video like to relate to this problem I'll call it Quadratic Equations real life problems or applications. But I think for this video, looking at the time, one problem is fair enough for this problem. Take a look at this problem. A backyard farmer wants to enclose a rectangular space for a new garden within her fenced backyard. This is the backyard, and the garden, enclosed garden right here. This is the garden. She has purchased 80 feet of wire fencing. So she wanna make this garden or design a garden like this in her backyard. She wanna use a fence right here, here, and here, and she's gonna use the back or the same fence from the backyard here. So only 3 sides. She's gonna use 80 feet of wire fencing to enclose 3 sides. That's this, this, and this. And she will use a section of the backyard fence as the 4th side. So this one is already covered. Find a formula for the area enclosed, this area enclosed by the fence if the sides of fencing perpendicular to the existing fence right here have length L. So they call this sides perpendicular to this side, the existing fence, L, and they call this side W. Of course you could call it whatever you want, but since I have a graph, I'm gonna stick to it and move on. What dimensions should she make her garden to maximize the enclosed area? Maximize. So we talked about parabolas, we talked about maximum, minimum, and this is what is gonna happen. Well, when they say maximize, that means the parabola is gonna up and down to speak maximum. Where is the parabola? We don't see anything. We don't see a quadratic equation. We're gonna use math skills and make it. Here we go. Now L plus W plus L will add up to 80 because she's using 80 feet of fencing. Simplifying by using math skills, L and L are called like terms, so I'm going to add them. 2L plus W equals 80. Now I could solve for W. Now I do have enough experience, as you could tell. I want to solve for W. W, it's easier to leave alone by itself, not 2L. I want to have an equation that has one variable, f of x equal, that's what we call it. X is my input and y is my output. Here I don't see x and y, but I want to make a connection between the whiteboard XY language in classrooms and the real life, which is now L and W. So here we go. W equals 80 minus 2L. Now, the other concept that we need to keep in mind, we need to maximize the area. So that's my main function. That is my function that I want to graph and take care of and maximize the area. So that's going to be my quadratic equation. Take a look and see how it's going to happen. We know that's L times W, since the graph says L and W, so I'm using LW. But I want to replace W with what I came up with from the restrictions or the given information on the side. 80 minus 2L replaces W. Using math skills one more time, doing the distributive, I have 80L. L times 2L will be 2L to the second. Of course, don't forget the minus sign. Rearranging it in standard form, it looks to me like speaking x and y, that this is like f of x equals minus 2x to the second plus 80x. And that's what I mean. Now it's math. This is real life. In real life, you don't see x and y. Their length and w and a for area and so on. So now I have a second degree standard form equation or function that has a leading coefficient which is minus 2, which means the graph opens down, which means we have a maximum at the vertex, and you know the rest. Let's save you some time and move on. I have the notes ready for you to finish the problem. A equals -2, so it opens down and we have a maximum. A equals -2, just stay focused. B is 80 and C is 0. The vertex is h and k, which is, in this case, it's not written in vertex form. We're going to use minus b over 2a to find the h component. Minus 80 minus b over twice a. Simplify, you get 20. To find k, you find the output of h. You plug in 20 in the problem. K of 20. It's supposed to be f of 20. Or the k value for the input 20. That should be, I would say, f. 80 times 20 minus 2 times 20 squared, which is 800. So that's my vertex, 20 and 800. To confirm and help you understand more about this problem and other problems, if you take your time, graph it. On the calculator it says x's and y's, but for us it's length. That's my input. X is my length, s, whatever the graph says, length, and output is area. F of x represents area. At 20 you have 800. That's the max. So when L is 20, you will have the maximum area here, which kind of makes sense. Take a look. It's symmetric. If you go 20 here, of course you have to go 20 here. That's already 40 taken out of 80. So you have 40 here. So it's going to be 20, 40, and 20. And if you do the math, 20 times 40, that's going to be 800. Now, let me also support that by showing this point and this point. Well, this point here says length equals 0. If you don't give anything to this side, that means you're not giving anything to this side, which means the whole 80 is going for W. You're not going to have any area. If you have no length and it's all W, that's going to be a 0 area. Where on the other hand, if you go extreme and you give L 40, if this is 40 and this is 40, that's 80 already taken away. You have nothing left from the fence to give W. So imagine a garden that has 40 here and 40 here, but no W, no width. That's not a garden to use. It's going to have a 0 area, and that's why here. So if you go extreme on this all the way, or extreme on this all the way, you're going to end up with 0 area. And right in the middle, that will give you the maximum area, which is more balanced and more decent. Just like something to talk about. So to summarize this problem and finish this video, which is about 50 minutes long, the maximum value of the function is an area of 800 square feet, which occurs when L equals 20 feet and W equals 40 feet. And that should do it for this video. And I want to thank you for staying with me for like about 50-55 minutes. Thank you very much. I'll see you in the next one. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.